I understand this is being recorded, so I have to make sure I don't suppress any malicious comments regarding other colleagues' work. Well, that's just a joke. Anyway, the title is given here. The outline of my talk is this. So the sections are going to be an introduction that's mainly aimed at people with no background in quantum field theory, or maybe just a rudimentary background. Then I'll talk about three properties of this so-called operator product expansion, which I'll explain. First of all, what it is, and these three properties are its convergence, its associativity, and another property that is maybe a bit harder to explain and will be done in due course. Okay, so before I forget to say, this is based on joint work that I've done over the years with Christoph Kopper as a professor at Polytechnic, and Jan Holland, who's a postdoc there. Right, so let me start off then with my introduction section. Okay, so basically I want to tell you what QFT is, or one version of what QFT is. So QFT stands for quantum field theory. And it is a theory that was developed in physics in order to describe properties of elementary particles that are associated with the fields of nature. Fields meaning here, you should imagine electromagnetic field or that kind of thing. There are many ways of going about explaining what this theory is, and many viewpoints on it. Maybe the most familiar one is a version of quantum field theory that lives in so-called Euclidean space. So and I'll focus on that setting. Definiteness. So the space that is, so in general would be a manifold. That is the underlying space manifold. So for the purposes of this talk, it's going to be basically always R4, but it could really be any manifold. There wouldn't be too much difference in the statements that I'll make, but they would be more complicated. So xi are going to be usually points in this manifold, and the objects one wants to study are expectation values of so-called fields. So the expectation values are some sort of functional integral, where the integral is over functions phi from m, to, for example, the real numbers in the simplest case. So you take these functions and evaluate them at these given points. And then you weight each configuration with a factor of exponential minus s of phi, and you normalize the measure by some constant, and then you integrate over all configurations. So you should think of this as some sort of integration measure, some sense. And S is an action, classical action. So I will from now on always be focusing on this relatively simple looking theory, where the action is simply the integral over the manifold grad v squared plus m squared plus lambda 4 integrated over the manifold. So, in case you have never seen this, so this is not an integral over space, but it's an integral over the functions on this space. So you take all possible functions on some space R4, and you sort of integrate over this huge infinite dimensional space of all possible functions. You want to evaluate this kind of observable for each configuration, and the configurations are weighted by this exponential, and Z is just a factor so that you get it's a normalization. You don't.
Surely you want phi on the left-hand side.
Sorry, on the left-hand side? Which left-hand side? Here or?
Yes.
So this is an expectation value.
But do you need phi? Because on the right-hand side you have the same phi, and integral over phi.
Yeah, so it's like in probability theory, you say you have the probability of some observable x, and then on the right-hand side you consider all possible values of this x.
On the right-hand side doesn't depend on phi, because you integrate over all.
Yeah, so yeah, if you don't like it, you just think of this as a function of x. So yeah, so that's if you like that better. That's anyway how probabilists will probably write it, and then I'm going to write it differently anyway. I'm going to write it in the way that physicists usually write it, as they think of it as the average of this thing, when averaged over all possible configurations against this measure, and this is then also called a correlation, Green's function or correlation function. Okay. Well, this thing is not too apart from the question where you put various phi's and so forth. Apart from questions of notation, really, this is not really well defined as a mathematical object, and that has to be discussed, or that does show up one way or another, and can't be ignored. Okay, so let's come therefore to the problems of this expression. So the problems are basically it's one and the same problem really. It's what is the nature of this measure, whatever. It's not really a measure anyway, so it's some formal thing. And also, what is the nature of the measure space itself. So in other words, when I integrate over functions, you have to be better make precise what kinds of functions. There are many mathematicians make a difference between many kinds of functions: smooth, piecewise smooth, totally irregular, analytic, whatever. That obviously makes a difference what you're integrating over. And so you should say that, and of course you should say what this integral really is. And that's a problem. So, however, in one simple case, you can basically you can solve that problem in one simple case, basically, and that case is called free field theory. So in free field theory, that's basically defined by setting this constant lambda that appears here, setting that to 0. And what happens then is that this action becomes a quadratic expression in phi, whereas before it was not quadratic, it's phi to the 4th power. So then S of phi is a quadratic form. And then basically I'm talking about a Gaussian integral, yeah? So because I have exponential of minus a positive definite quadratic form, that's a Gaussian integral. S is just Gaussian integration. So everyone knows how to do this. So if you do a Gaussian integration, what comes in when you integrate against some sort of monomial or polynomial in your variables, just think of the analog where you have a Gaussian integral of a finite dimensional space. What comes in is usually the inverse of the quadratic form. That's up in the exponential, and that's called that has a name. It's called the covariance, and it's just in this case minus the Laplacian plus m squared minus 1. So well, you probably know Gaussian integration on a finite dimensional space, so this is just the same, just on an infinite. You just use the same formal rules as well. Mathematicians have worked it all out, and I won't explain it. But the interesting point that you find is that this measure is supported on distributions. Right. So what does it mean supported? Basically, I mean, informally speaking, you can ask, this kind of sort of summing or integrating over all configurations, and you give each configuration a weight. And of course, if the S is very large, the weight is very small. And so if you have a very irregular function, then it means the gradient is very large. So the S is very big. So minus S is very negative. So e to the minus S gives a very small weight. So you give a very small weight to irregular functions, but still you give a non-zero weight to them. So in fact, even it turns out that even distributions are sort of integrated over. They carry a non-zero weight in this integral. Yeah? So you can't just say, well, I'm going to integrate over smooth function configurations or piecewise smooth. Then you'd make a big mistake in this integral. Yeah? So you really have to integrate over very irregular things too, and that creates a problem.
Yeah. Compatible. Sometimes this integral is computed. Imagine you have a nice smooth manifold, then you can decompose functions into harmonics, smooth functions.
Yeah.
And then you would define this measure as
the
coefficients.
Well, you can Fourier decompose a distribution too. Then that's compatible with that.
But still, if you do Fourier decomposition,
it's just a different. Well, the Fourier coefficients would be arbitrarily large, would not be dampened for large eigenvalue. Okay, so the
Gaussian integration. Do you also mean some relation with the Salina integral and find cuts formulas?
Sort of, yeah. It is related. Yeah, there's a whole story how it's related. And I mean, it's not the main topic of the talk. I'm just going to give you some intuitive idea of these things. Yeah, so now let's though think of this case as solved and look at the interacting case. Interacting fields. So that is the case when lambda is not 0. And in fact, you get a sort of a positive action because you want to put it minus s in the exponential. It better be positive. So let's look at that case. Now then, it's basically not known how to make sense of this measure. It's just not known. It's too complicated, and probably it cannot be done. But what you can do is you can try to solve this problem by expanding out this nonlinearity in the following way. So then sort of the measure is not known. By that I mean not known. I mean people don't know how to make mathematical sense of what this is supposed to be. But what does make some sense is what you can do is you can say that S is S0 plus lambda S1, where you just say S0 is the part that you know how to deal with, namely this quadratic part that gives S0, and that S1 is this e to the 4. Yeah, integral of that is S1. Okay. So and then what you can do is you write S, you substitute S in the exponential by S0 by this, and then you keep the S0 where it is, and you Taylor expand the part of S1 in lambda. Yeah, so you just do a Taylor expansion of this exponential. Everyone knows what that is, I think. And so if you do that, you get the following formula for these correlation functions. It becomes a sum, infinite sum. It's just a Taylor series. And then n, and then this is the expectation value with respect to the free series, so where the S is replaced by S0. So that I told you can do basically, and then you have this, but you also have n times this integral, yeah? So you have to n 1, 2, 3, n factors of this. So that's just, you get that, as I said, by just formally Taylor expanding out this exponential, and that series is called the perturbation series. With the idea physically that lambda is a very small quantity, and so hopefully in practice the first few terms would already give you a reasonable approximation. Okay, now there's a problem with this, and the problem is precisely that, as I said, this Gaussian integral that really defines this is supported on distribution. So in order to form this, you have to consider configurations phi that are distributional, so you have to take a distribution and then raise it to the 4th power, and you of course have to do that with any distribution and then sum up, and you can't form the 4th power of a distribution. It just gives you nonsense. Yeah? So sometimes you can, but in general it just gives you nonsense. So this gives nonsense, and you also find that if you just apply naively the rules of Gaussian integration, even if you never heard of distributions, or you have heard but don't care, then you still find that there's a problem, and the problem just shows up maybe in slightly different ways. Okay. So of course this is a known problem, and there's a way of solving this. So this is basically ill-defined. So basically everything about this is ill-defined. So first of all, the integrand, if you forget about this integral, then just think of this as, you pointed out, a function of x1, x2, xn, and y. That's not defined, it's just not defined. So even if in some sense you could somehow make sense of this as a function, then you would have to do these integrals where y, so you have n copies of this where y is integrated over your manifold. That also wouldn't be defined, because M in our case is R4, and R4 is a non-compact space, and usually this just doesn't converge. Yeah? So it's the first problem that is not defined as a distribution is a UV problem. This is an IR infrared problem. So these are two reasons why this is nonsense. The third reason, even if the first two problems were absent, this still would be nonsense, because you cannot sum this series in the end. It's just a divergent series, even if the individual terms are okay. So it's basically complete nonsense. So it's a mystery at all that people were able to make progress on this, but of course they were, and otherwise I wouldn't be here. So I can't explain how that is done. So So at least part of these problems, some of these problems can be dealt with. So renormalization is basically the way in which you actually make sense of the integrand. Yeah, so that in principle you can, if M is compact, you can then integrate over everything. And that is, the idea is basically that you, well, it's not that easy to explain, but the one way to go about it is to take this covariance and to change it somewhat. So the covariance was here. So that basically corresponds to the quadratic part, quadratic form in the action. So you change that to something with a so-called cutoff. So lambda is just some number less than infinity called a cutoff. So if lambda is infinity, then you're taking e to the formally e to the 0, and then the exponential is 1. So you don't have that, and you have the covariance that you started with. But if lambda is not 0, then it turns out that if you translate this back into your rules for Gaussian integration, whereas before very irregular configurations phi at a non-zero weight, now because of this thing, this gives a makes the weight makes the weight of irregular field configuration to 0. So you only basically now integrate over smooth field configurations. You can say that, and then of course for a smooth function you can say what the fourth power is, and it's reasonable to expect that it's okay, and it is. Yeah. So, and also even if you don't know this in fancy math, you just do a calculation, you find that now you don't have a problem. Okay. So at least the integrand is defined, and then if M is compact, the integrand is defined. The divergence of this series in capital N, you just can't do anything about that. That's just divergent. So you can't. So you can still talk about this as some formal power series. So the individual terms, of course, highly non-trivial, and you can talk about this and whatever its properties are in the sense of formal power series. So you've introduced this cutoff. Of course, you don't want to keep it, because then you've just done something different. I mean, that sometimes people do that. They just can't solve a problem, and so they change the problem, and then they claim then they solve that. But of course, that's no real progress. So you have to, of course, take this lambda to infinity in some way. And of course, if you do that naively, you get back to the nonsense that you started with, of course. So you have to do that in a smart way, which is then this process of renormalization, and that is as much as I'm going to say about that.
May I just ask, I'm not really an expert of physics, but as far as I understand, there are like several dozens normalization methods, and you have to choose the right method for the right problem. And only physicists can tell you which one to choose.
No, I think that's a bit the wrong. So you can you can say, well, you can go about it in say that you first, like mathematicians sometimes do, like when they define the Chern character, you can say, well, I want something called the Chern character, and I'm now going to draw up a big list of things I want, and then I'm going to give you a construction, or maybe there are 7 equivalent ones. Okay, it's similar here. You can say, like, look, this is ill-defined, but I just from the formal properties, I want this and this and this and this properties. And then there's a big theorem that there exists a way to do it, but it's not unique. And that's your different choices. And in fact, you can characterize very precisely what are the different choices. And you don't need a physicist to tell you. I mean, the mathematician can tell you as well something. Okay, so then you have to fix your choice. You have to your choices correspond to some free parameters some finite number of free parameters, which you have to fix by some conventions.
Physical point of view, you need to get the right answer.
Well, yeah, and you do. I mean, it's not what right is. I don't know what you mean right. I mean, you have a formalism, yeah. So you have you get the physicist, the experimentalist will tell you 4 parameters, 4 physical observations that will fix your parameters, and then you feed that into your theory, and then everything is unique. Okay, so you get unique answers for any other thing you want to calculate. Anything. Okay. Right. So that was sort of my. So now I'm going to come to this thing called the operator product expansion, which is the actual topic of my talk. Okay, so what's this? So you can consider things like a composite field, so that I'm going to call OA in the following, and that's basically an expression like this, M, and then so A stands for. Okay, all you do is you just take these and you take derivatives and you multiply them together. You wouldn't, and you just call that a composite field. That's it. And I'm just going to because I don't like to write this all the time, and just call them OA, and A is supposed to incorporate all the information. Just this is a tensor, of course, and so it's just a compact notation. And you assign a dimension to each such thing, which I'm going to call bracket A, and you think of this as a dimension, or engineering dimension. So A, and that in 4 dimensions, this is 4m plus the sum of all these. Okay, so it's physically motivated, but you made just a mathematical definition. And now what's the operator expansion or operator product expansion? That's the following. Is the statement that if I have some of these things, L1, X1 through OA and Xn, and then times a couple of other guys, J equal 1 to S. So you take that, and then you say that's approximately equal to a sum of other things, where I sum over all composite fields having dimension less than some number delta, and then there's some coefficients A1, A1B, and then the same thing, J. Okay, so these things are called the OPE coefficients, not OB, OP. And these things are called the spectators. And the idea is that this is an approximate equality. I'm going to say more about that in the limit when xi goes to xn for all I. So you have some point xn here, and then you have these kind of guys sitting around, x1, x2, and x3, say, and you have some spectators, y1, y2, and so on, and they all rush to this guy, and the spectators sit there and watch. They don't do anything. Okay, so the statement is that in this limit, this is well approximated by that, provided the delta is chosen sufficiently large. So you should think of this delta as the order, just like the order in a Taylor expansion. So in a Taylor expansion, you expand a function around a point. So the point around which you're expanding here is this point xn. And in a Taylor expansion, you think of the other things being close to the reference point. And then you have an order to which you expand. But in the Taylor expansion, just a number of derivatives you carry. And that you should think of this delta. And this C is, though, I mean, that's where the analogy ends. So the C's are very non-trivial functions that will depend in a complicated way on the original action. Yeah, so it's difficult to calculate. Okay. I haven't even told you how to calculate this, but I assume you can. But these are sort of the things that are the OPE coefficients that are independent of S and the spectators. Yeah. So that's at least the statement, and it was it's been suggested a long time ago by a guy called Wilson, I think around 1970, if not exactly. So he said that maybe the correlation functions should have that property with certain coefficient C, and then a guy called Zimmerman had an idea how to calculate the C's in this perturbation expansion. Yes?
Do you only consider operators containing factor 4s, or where does the 4 come from in the dimension of the operator?
No, 4 is the, sorry, so no, sorry, that's not 4. This one is just M, sorry. Yeah, so each field phi has a dimension of 1, and then because there are m of them, you have m, and each derivative has a sort of dimension of 1, and then you add that. Thanks.
What is the delta?
Yeah, as I said, the delta is some number that you choose. It's sort of to make the approximation better. So just like in a Taylor expansion, by going higher up in the Taylor expansion, you make the approximation better. You can do so here as well. So more precisely, if you take the left side and you subtract the right side, then the remainder will be sort of the order of the difference between these points and the reference points to some power, and that power depends on how high up you went. Just like in a Taylor expansion. I mean, this is not a Taylor. I mean, in no way this can be explained by just an analogy. Yeah. Okay. So the questions that I'm going to pose, and these questions correspond to these 3 points precisely, are the following ones, and I'll pose the questions and provide answers. So, in what sense is this OPE convergent, or a good approximation? I've been very loosely talking about is a good approximation and so forth, and I'm now hoping to make this more precise. And so, second question, in what sense are the C's, by C's I mean these coefficients, like the structure constants, constants of an algebra. And the third question is how to characterize perturbation theory in terms of the C's. Okay, so, coming to 1, which is also my next section. So, convergence. Okay, so I'm just now presenting you the mathematical results. Of course, this I don't think you can fully really understand this because I haven't really told you how to get this. See what's the procedure, what's the calculation you have to do sort of to get them, but just assured you that there is one. And now, but assuming, given that we know there is one, you can still ask whether, into what sense this is a convergent series. And so that's my first theorem. Because I'm a mathematical physicist, I like to prove theorems, and it's theorem 1 because it's in section 1, and so it concerns the size of the remainder or in this OPE at perturbation order L or loop order. Okay, so I should maybe say what I mean by perturbation order. So as I said, my theory, my action depends on this lambda, and therefore since the coefficients belong to this theory with that action, they also depend on lambda, and the perturbation theory means I expand this in lambda around lambda equal to 0. That will correspond to the free theory, and then I have various orders. And of course, as I said, the series doesn't converge, but I can still ask whether this is a good approximation at any given order. Yeah, so that's what I'm saying. So I fix my order to be L. So L can be anything. L is sort of the loop order, if you like, the number of loops you carry in your Feynman diagrams. If you choose to calculate these C's in terms of Feynman diagrams, as you can. So then you ask about the remainder. The remainder is what you have when you take the left side and just subtract the right side. That's what is left, just like in a Taylor expansion. If you truncate the Taylor expansion at some delta. It's not the exact result, it's just an approximation, and the remainder is the error you make. Yeah? So the error, and the idea is of course that this error should be small, of course otherwise the expansion is no good. And so I'm just because physicists like to do this, and because also it makes the meaning of the result much more transparent, you can take this and actually Fourier transform the spectators in Y. That's just like working in momentum space for the so-called external particles. J, and same here. Yeah, so you just take this identity and Fourier transform both sides in the variables J, and you get P, so that's all. And then consider the remainder then as a function not of the Y's, but of the P's. It's better. Okay, so there's a bound, because you can, if you have any kind of experience with this, you will know that you just cannot ever hope to calculate this exactly. So what you can do though is you get a bound. That's good enough to understand many of these properties. So a bound means that you get a less, not an equal sign, but a less than or equal sign. So you get the product over all these dimensions, AI, and factorial. Take square root of that, and then you have a k, constant k, times m, times the supremum of 1 and all these momenta. I'm going to write p divided by m to s, the number of spectators, plus 2l plus 1, and everything raised to the power sum of ai plus 1 plus delta. So the point is not to write some arbitrarily complicated formula, but one that which I'll explain what these things, how you should think about these terms. And then it goes on, 1 divided by the square root of delta factorial, and then k times m times the supremum of xi minus xj to some power I plus 1 plus delta divided by the infimum of xi minus xj, I not equal to j, raised to the thing, another power I plus 1. And then there's a last contribution times P over the infimum of M and some quantity called eta of P raised to some power 3s. Okay, so now I give you an explanation of these terms. And these, so first of all, we could ask whether the expansion converges, and so a series converges if the remainder goes to 0. So the remainder should go to 0 as this delta, the order to which I expand, goes to infinity. And so if we look how these things depend on delta, so delta dependence is basically this. It's basically this thing here, 1 over delta, root delta factorial, and then times some constant to the delta. So it's always here up in the exponent. So you know that factorial always, even if you take the square root, that doesn't make it any difference, goes to 0, is growing much faster than any power exponentially. So this just goes to 0, yeah?
I'm confused here, both L and delta.
Yeah, delta is, L is the loop order, and delta is the order to which you expand out the operator expansion.
What is K?
K is a constant, I'm writing it K because I'm German, and then constant is K. K constante. Like K series and all these German things are K.
So presumably it's crucial that this theory you're working with is renormalized.
Right.
What was capital S?
S is the number of spectators, the number of particles in your state, so to speak. So okay, so that is convergence. So that's it was a really new thing that people always said it's maybe only asymptotic. It's really convergent, always convergent expansion. It really converges. But that's usually nothing converges in quantum field theory. So here's something converges. So that's explaining the first part. And now you have to ask about the rate of convergence. How fast does it converge? So it converges, but it may not converge very fast. So the rate of convergence is affected, for example, by this ratio here, the supremum over the infimum. So what does that mean? So the rate convergence is slow if, so there are basically two cases. So if we look at this factor, so let's just draw this. So let's take 3 points, x1 through x3, so product of 3 operators. So I'm going to draw these points as 1, 2, 3 in some sort of triangle. So if the triangle is very degenerate, like this, and has a very short side and 2 very long ones, then the convergence is slow. Whereas if the triangle is more like an equilateral triangle, then this ratio of supremum is basically, the supremum is the longest distance over the shortest distance. Yeah? So if all of them have the same length, it's a number of order 1. If two lengths are very much bigger than the other, it's a very large number. So large numbers are bad for convergence because then this constant is very big, and it takes a long time before the factorial wins. So basically the points, the relative position of the points matters. And what also matters is the magnitude of these momenta, that you have the momenta of the external part of the particles. So it's slow if that is the case, or if the pi's are big. Okay, well then that's quite obvious because you have this p, norm of p is sort of a typical size of the p, sort of the maximum p basically. So that is then a big number again, and you have to wait a long time before you converge. Okay, so there's this last factor. So this basically explains the first two lines. The last line is explained as like this. So this has to do with the infrared behavior and really concerns the behavior of the theory for small mass. That's an interesting limit in quantum field theory.
So M is the mass.
I'm always working with this. Sorry, my action has to be still up there somewhere. So no. Yeah, M is the mass of the field.
So you need to have everything massive. If you have something massless.
Yeah, so that's all I'm getting to now. If I want to take M to 0, then it may be that this denominator becomes very small. Now I have to say what this eta is. So eta is basically you draw tree diagrams and maybe, so you have the p's going in somehow. You draw all possible tree diagrams, not loops but trees, that's important. And then you have at each node, you impose a momentum conservation rule so that higher up in the tree you get the next momentum by condensation. And the eta is the minimum of the flowing momenta in the tree. Okay? It's minimum of flowing.
The full valid vertices?
Basically, yeah, 4 valid, but except the operators may have higher valence. The operators, of course, can have.
The valency has to do with valency of the.
It's related to the valency of the interaction and so forth.
Another question: does coupling constant play in your system?
Yeah, it's at loop order L. So if you want to get, so basically it's the lambda to the L order basically of this whole thing, roughly. So what that means is that in a massless theory, these things better not become 0, and that has to do also, you see also in amplitudes, if some of the momenta of the particles become collinear, then usually the amplitudes start to diverge in a massless theory. Yeah, so it reflects that kind of behavior. So divergence for exceptional, they're called exceptional configurations. Yeah, exceptional P's. Yes. 0. Yeah. So I want to convince you that while this is not an exact formula, it's a bound that tells you many qualitatively important things about this expansion. Yeah. So that's my point. And I'm not going to tell you how you prove that, and so that's very complicated and sort of something I did with this gentleman mentioned first, some work that evolved basically over several years in papers and so on. Gradual technical improvement and so on. So let me come. Yeah.
For m equal to 0, there is no estimate, because this one does not work.
For m equal to 0.
Zero mass.
Yeah, for 0 mass, basically the point is that these correlation functions then become distributions in p, so you can't really think of them as being at fixed p, so you have to average over the momenta, and the exceptional momenta are sort of measure 0 set, so it doesn't really.
So is there some result for 0 mass?
Yeah, it is. I mean, then you have to just take this and integrate it over p. Yeah, so you don't consider particles at sharp momenta, but sort of particles that sort of more like wave packets. Which you should do that anyway, but it's a bit harder than to write out what these things are. Okay, so now I should talk about the next point, which was point to associativity.
About this theorem, is it your theorem?
Sorry?
This theorem, is its proof due to you?
Yes, but
It's a method of the proof. Is it, could this theorem, for example, have been proved already in 1970s?
no, I don't think so, because I mean, as I said, it's based on an approach to renormalization called the flow equation method. It's due to Polchinski originally and Wigner and Wilson also, but it involves many technical improvements of this, and so it's sort of a gradual the gradual improvements sort of finally enable you to do something like. So it could have definitely not proved, I think.
So it became possible due to gradual technical improvement in the theory.
Yeah, well, you could say, and you want to, also have the idea in the first place that this could converge. I mean, people would have not said that it would. I think in 1960, well, in 1970, I guess is right. They would not have thought, I think, it could converge.
Is there any convergence in the loop order?
No, that always diverges. So, but that has nothing to do particularly with this OPE. That's a general phenomenon. Yeah. So that has to do with non-perturbative effects, which are not taken into account. Yeah. So, but that you have in basically in any calculation of anything. Yeah. So it doesn't. Well, in any, basically a series in lambda, perturbations in lambda always diverges, basically, anything. Okay, so now let me come to the associativity. And I think I'm not going to come to point 3, but so I'm going to leave it with point 2. I guess that's partly. Okay, so if you look again at this OPE, which is right there at the top whiteboard, the bottom line, and you think of these C's, if you look at that, what immediately suggests itself is that the C's are a bit like the structure constants in an algebra. So if you have an algebra, you have something, you write generators TA, and you multiply them, and then you have something like this, right? And these are the structure constants, these little c's. And the idea is pretty much that the TAs should be something like the OAs, and the CABCs should be something like the CABC now of x1 and x2, and so on. Yeah. So you still have these spectators and so on, but if you just erase this, because it's valid for all spectators, basically it means it's an operator. People say it's an operator equation. Yeah. So that suggests that this C's should be basically a bit like structure constant, just by writing that way. And that's of course an old idea. But the question is precisely what does that mean? So the key properties of structure constant, the key thing that they have to satisfy is the Jacobi identity, of course. So you know the Jacobi identity. Okay. So the question is, do these coefficients also satisfy some sort of Jacobi identity? Now, one thing you note is that the C's, you don't have things just with 3 indices, CABC, but with n, capital N indices, n plus 1. Yeah? So in that sense, it still is a bit different. So in principle, in an algebra, you could have that as well. You can of course take a product of 3 things, or 4 or 5 or whatever, any number. But in elementary school, you don't learn like the product of 2 numbers, and then in 2nd grade, the product of 3 numbers, and 4th grade, product of 4 numbers. But you learn that once you know how to multiply 2, then 3 and so on, you just do it inductively. But that's not so clear for the C's, so that's a bit different. So in fact, the kind of associativity that can be shown to hold, I'm going to write this down now without further ado, is like this. And you can convince you that it is sort of like associativity. So again, that's a theorem. You can factorize this as sum over C, CA1 and B, C, yes. So that's a absolutely convergent series. and provided, so you can again have to form this quantity I'm going to call epsilon. It's the minimum of 1 less than or equal to I equal to m divided by the maximum n plus 1. Sufficiently small. So what does this condition mean? Well, I'm going to explain this and then I think I'll stop. Okay, so I remember I drew these triangles. They're still here. So epsilon just basically, you single out a subset of points like these. They will correspond to, in this example of 3 points, to these two that are closer together. And then you form this quantity epsilon, which basically tells you how degenerate this triangle is, because it's the minimum distances within this group divided by the maximum distance of the thing to the rest of the group, if you think about it. So epsilon would be very small in this example, where this would be m would be 2, and epsilon would be of the order 1 in this example. So I'm telling you that in this case, where the configuration of points becomes very degenerate, it's okay if you have a product of 3 operators to first expand the product of the first 2 and then the rest. So expanding the first 2 first and then the rest corresponds to, if you write it all down, corresponds to this side, and expanding them all at once corresponds to this side. And the fact that it's the same implies some sort of associativity. Right. Of course, you can have many ways in which some group of some points are closer to each other than the rest. Yeah. So therefore, it's not like just one associativity condition, but a whole hierarchy of self-consistent conditions. So in this sense, again, so this is again complicated to show that this really converges in this. Okay. So my last point, which I won't mention because I'm out of time, is the question as to how to calculate these. So the traditional method is to look at this defining equation up there with the correlation function, then calculate the correlation function, and then ask yourself which c's do you have to put there so that the left side approximately equal the right side. Yeah? So that's a traditional way of doing it. So, but my viewpoint on quantum field theory really is that just like an algebra fundamentally is defined by its structure constants, a quantum field theory fundamentally is defined by its constructor constants, which should satisfy relationships like this. And so if that's so, then perturbation theory should not depend on crutches like these correlation functions, but you should be able to do that directly with the C. So meaning that you first need a starting point, which would be the free field, and then you should be able to have a self-consistent way of determining order by order the C's to higher order. And that is indeed possible and would have been the topic of my third section if I had time. There's a beautiful recursive formula which can be used to determine the OPE coefficients from a given order from the lower ones without any of these conditions, and that beautiful formula was found recently by us in a paper. Okay, well, I guess I'll stop here and I'm happy to get further questions, answer further questions.
Will it take a lot of time to write that?
Well, no, yeah. So it's. I don't think it's given that the C's are a bit long, and it's. But I can write it. It's okay. So basically, the idea is, of course, C. All the C's are functions of lambda. Yeah. So you could expand this out in a perturbation series. C naught plus. Okay, so then this would correspond to the free field. This would be the one loop correction. This would be the two loop correction, and so forth. And so I would like to express C1 in terms of C0 and then C2 in terms of C1 and so forth. But alternatively, I can just give you a differential equation in this lambda, because that will also do the same do the same job, and that's easier to write. But I could also write the recursion. It's the same. So the differentialist equation is if I take d by d lambda of a coefficient. So this depends on endpoints. Now I'm writing explicitly that it depends on lambda. I mean, it depended on lambda all the time. I just didn't write it. So if you write out that in terms of a power series, that will give you the next higher order if you know the lower orders, right? Just because taking derivatives reduces the power of lambda by 1 unit. Okay, so you need to write this in terms of the c's without a derivative. That's the idea. So and you do that. You integrate over a point y, and then you have a function a1, an, and then right somewhere the interaction has to come up, because you're talking about phi to the 4 theory, not of some random other thing. So it comes up, you take the OPE coefficient with one more operator, and that new operator you put is phi to the 4. That's your interaction. And so x1 through xn, and then the last point is y. And then you have to take away minus the sum into n, and then c less than or equal to 4, c a1, c an, x1, c y aj phi to the 4 c j y, and then there's another similar term like this. I'm not going to write it down, but it looks just like this, and the explanation is the following. So if you know your Lagrangian perturbation theory, then usually when you take a derivative with respect to a coupling constant, you get down the operator corresponding to that coupling constant, and that which is phi to the 4. So that term is kind of, you would guess that. Okay, that term, so now if you were just to take this and integrate it over y, if you didn't have the others, that will have very strong singularities as y approaches any of these other points, and so the integral would diverge. You know, so there would be x minus y to some very high negative power. Yeah. So that would make no sense at all. But you know, because of the factorization, if x is very close to, let's say, xn, it factorizes, and so this term corresponds precisely to take away the factorized contribution for small distances. And because y can be either close to xn to any of the points, you have basically this number of terms. And actually you just need to take off the most singular parts. That's where this restriction c less than 4 comes from. So this takes care of the potential UV divergence, and there's another term which takes care of potential infrared divergence, which has precisely this, again, factorization. So I think this is a very beautiful formula, and if you want to solve it recursively, you make this expansion, you plug it in, and then this gives you C1, and then on the right hand you have just C0s or C2, and you have C1 and C0 and so forth. You don't.
It's the recent formula you mentioned.
Yeah, it's the recent.
And whose formula is this?
Mine.
This still works for weakly coupled stuff, right? So lambda has to be reasonably small for that.
Right, so it's a perturbative expansion, so you generate the higher and higher terms in the perturbative expansion, but I expect this formula to hold also non-perturbatively, yeah? So I believe it's a true formula, even non-perturbatively. I just can only solve it order by order, that's the point.
Where are the UV divergences here?
No, they're automatically, it renormalizes itself automatically. That's the beauty of it. There's no external wizardry that that has to be applied that comes from nowhere. It's just everything is already self-consistent. So you don't have to learn renormalization, it does it automatically. Yeah, so as I said, the UV divergences would be precisely when y becomes close to one of these points. That's also the same in Feynman diagrams in position space when points come. So there you have to, by hand, introduce counter terms to get rid of it. Yeah? So here the counter terms are already there. They're not introduced by hand. They just come out. They're just there. They have.
In the other recipe of counter C's, there will be UV divergences on both sides.
Right, but everything is the renormalized quantity, so it's not the bare quantity. So
then things depend on the cutoff. So are you saying that?
No, the cutoff is taken away. It's sort of taken away. So everything is after renormalization. Before renormalization, everything is just formal. You can't prove anything. You can just prove infinity less than or equal to infinity. Something like that.
Physical renormalized.
This is physical renormalized things. So the ambiguities correspond to the possibility of making field redefinitions for the operators. That's a field that kind of thing.
So what do you expect this to hold non-perturbatively?
Why?
Yeah.
I don't see any reason why not, because well, I don't have a non-perturbative alternative definition, so I don't know. I can, but you see, it's an equation that holds order by order. I don't see what possible. I mean, it's just like if you ask whether the Schwinger-Dyson equation should hold non-perturbatively. People would probably say yes, but of course you can't check. You can't check it. Well, yeah. So you can take it as a. Of course, it's an equation. You have to show it has solutions, right? And so in practice, the way you get a solution is by making this expansion and plugging in C0 from the free field theory, which you know. But if you had a way of showing otherwise that there exist solutions, then that would be the non-perturbative definition of the theory.
In this formula, what is the set of which series is to
The same as before. So all O's are just the same things.
How much is it?
Well, it depends on the dimension, right? And at dimension 1, you only have phi. At dimension 2, you have phi, grad phi, phi squared and grad phi. At dimension 3, you have grad squared phi, phi grad phi, and
gradients and anything.
it's just a combinatorial problem. So it's a counting you can estimate it with Ramanujan's formula, the number, for example. Yeah? So some partition problem. Yeah? So standard combinatorics.
Are these three theorems that you described only for Euclidean space, or is this general?
Yeah, so the approximations, I'm definitely making use of the fact that I'm in Euclidean space. And so in Lorentzian space, of course, that's the magic of special relativity, yeah, so that the distance can be nearly zero for light-like points, but points are not actually, you don't think of them as close, but the physical distance is zero. So there, this expansion holds either when you approach from each other from space-like points or when you go onto the light cone. That's also then. But you have to say a bit more precisely what you mean, because these distances that I've wrote with modulus of that were Euclidean distances, and you have to.
There's some results about uniqueness.
Yeah, so existence is basically because you already have an independent construction of the C, so basically you show that construction satisfies that equation, but you can turn it around, of course, that's the idea, and generate the new by just plugging this in. So if you just feed in C0, then you have a quadratic equation involving C0 on the right side. You do this integral and you get C1, and so you automatically generate the solution that way.
Did you think in direction, this is a scalar theory, right? Did you think in direction of introducing tensor indices, for example, the N-Mills?
Yeah, yeah, of course. Yeah, I think the subtleties that were these estimates, I think the tensor indices do not make it that hard. Of course, the local gauge invariance adds sort of one additional layer of complexity, so you have to use this BIS method, and you would use the BIS method.
Mass, did you need mass here? Or
No, that's the point. I mean, that's why I was careful to write this complicated bound that you can also holds in the massless. So you would need that definitely because you have a massless particles. Yeah, no, that's a good point. So you need really the full glory of the full.
Any more questions?
What are the advantages of these OPUs in relation to other?
Well, my view is really there should be sort of a definition of quantum field theory. That's more if you do, I don't know. I like to have think it that way. Of course, this expansion is used by practitioners a long time. Has been used for many years. So when people, I mean, it's basically the most in QCD. People like to calculate something like, let's write it this way. So, and then P. So P is like a state for proton, yeah. So like a hadronic, and J is a quark current. So J is something like Q bar gamma mu. Something like this, and well, you'd like to know what this is because it's an observable basically, yeah. So the problem is the proton. It's you can't calculate anything about the proton in perturbation theory. Yeah, it's a bound state, of course. So what people do is they basically say that, well, you apply the OPE. So the P is basically like the spectator field. Different way of saying this. So you say that this is the sum over operator C with some OPE coefficient J mu, J nu, C. Well, one point is X, the other is 0. So yeah, it's by translation invariance. You can of course always do that. And then you have some operator P, OC of 0, P. Yeah. Okay, and then you say that basically this is non-perturbative. You can't calculate it, but so you just make some ansatz. So it's a function of P and C, so FC of P. It's called a form factor, and so the form factor, again, I said you can't calculate that in perturbation theory, but you can just, you know, it's the proton has a momentum, so you can parameterize that by a few parameters, but these you can calculate in perturbation theory because they're short distance for small x, so hard collisions. That means x is small, then the coupling is small, then this can be calculated, and that's how people actually calculate these things. So it is used in practice. It's not just, it's really used in practice. Yeah. So.